Hello students, today we will see relation between angular momentum and moment of inertia. So already when we have learned the cross product, we have learned about the angular momentum, that the angular momentum is cross product of perpendicular distance from the line of action of momentum and momentum. So L is equal to R cross P. And if we just see the magnitude of angular momentum, that will be equal to, RP, that is equal to RP sine theta. If theta is 90 degree, this will be equal to RP. Okay, the angular momentum is equal to RP, where R is the perpendicular distance from the line of action of momentum and P is the momentum here. So now you will see that we know the momentum P is equal to mass into velocity, and if we replace here, the angular momentum will be equal to P if we replace with mv, so it is Rmv. The angular momentum will be equal to Rmv, where R is the perpendicular distance of line of action of momentum, m is the mass, v is the velocity here. Now we know that the linear velocity, this v is the linear velocity, and linear velocity is equal to radius, or you can say this distance r which we have taken, about which the object will means the torque will produce and the object will rotate. So r, v is equal to r omega. Now we'll place the value of linear velocity v with r omega, then it will come r omega. So the angular momentum is now equal to mr square omega. And one more thing that we know here, the moment of inertia I is equal to mr square. So we'll say this is L is equal to I omega. That means the angular momentum, you will find here the angular momentum is, here is equal to what? It is equal to moment of inertia multiply with angular velocity. Okay. Now after that we'll see the law of conservation of angular momentum. For law of conservation of angular momentum, we know that if tau external, the total torque is equal to tau external plus tau internal here, and for an isolated system we know that all the particles apply force on each other, so all the internal forces will be cancel out, and so this internal torque is also cancel out. So whatever is there, the total torque is equal to tau external. And in such situation we know that if tau external is 0, if tau external tau external is 0. In such situation, we know that the dl upon dt, that means the angular momentum, derivative of angular momentum with respect to time, give us tau. This formula already we have derived there. So this tau is tau external here, and tau external is 0. So this is 0, and in such situation L must be constant. Any quantity, the derivative of any quantity is 0. That means that quantity must be constant. The meaning is that here, for an isolated system, if tau external is 0, in such situation, that means obviously if tau external is 0, the body is isolated, means the system is working inside only, all the particles are applying force on each other, and the system means no external tau is there on the system, and in that situation we know the angular momentum would be constant. Angular momentum would be constant. Just now we have derived another formula of angular momentum, that is I omega, that means the moment of inertia and the angular velocity, and this would be also constant. This would be also constant. The meaning is that if no external torque is applied on any of the object, that means the body is separately or isolated body, in such situation the product of I omega would be constant, which gives us the angular velocity, that is L. Now you will see that if this situation means when L is constant or I omega is constant, if you increase moment of inertia, automatically the angular momentum will decrease, and if you increase angular velocity, then automatically this moment of inertia will increase. So means if one is increasing, the another factor will decrease, and if this is increasing, this will decrease. So that means anyhow the product of these two will give us the constant quantity if no external torque is working on the system. And this, the law of conservation of angular momentum, has great application, and we'll see in the next part. Now we'll see application of law of conservation of angular momentum. The first application is a ballet dancer can vary her angular velocity by outstretching her arms and legs. You can see here a ballet dancer means एक ballet dancer अपने angular velocity को increase और decrease कर सकती है अपने arms को outstretch करके या उसको fold करके. For example, you will see here this girl when she is outstretching her arms and legs. So this is the rotational axis, and from the rotational axis this distance will increase, the distance of the mass will increase, and from the rotational axis, this is the rotational axis, and the distance of mass will increase, suppose this way, okay. So r this r will increase, and that will increase the moment of inertia, because moment of inertia is mr square, and the moment of inertia will increase. So according to law of conservation of angular momentum L, I omega would be constant and I is increasing, so automatically the omega, that means the angular velocity, will decrease, okay. And what happened when she fold her arms like this, arms, and she bring bring her leg close to other leg, so the angular velocity increases, and on account of decrease in moment of inertia. So in such situation, this is the rotational axis, and the distribution of the mass from the rotational axis will decrease, and r will decrease. If r will decrease, so the moment of inertia I will decrease, and because moment of inertia I will decrease, this L is constant, and the product of this two is constant, one is increasing, one is decreasing, so automatically the omega will increase. The omega will increase. So when she bring her leg close to another leg and fold the arms, so automatically the angular velocity will increase and she will means rotate very fastly. So this way a ballet dancer can vary her angular velocity. Okay, another example we will see here, that is of the neutron star. Means here you will see, when nuclear fire in the core of a star burns low, the star may begin to collapse, ultimately becoming a neutron star. During this process, the star is an isolated system and its angular momentum L cannot change. As the size of a star decreasing, its rotational inertia I is decreasing, and therefore its angular velocity will increase greatly. So in case of the neutron star, this way actually means the inner core, the fire is there and in that case this will means the size of this star will decrease, and because the size is decreasing, so from the rotational axis, from where it is rotating, from the rotational axis, the distribution of the mass will be decrease, and because R decrease, I also will decrease, and it is means this type of a star is an isolated system. Means the angular velocity, angular momentum will be conserved, and since I is decreasing, omega will increase greatly. So this way the neutron star means when it is collapsing, the angular speed will be very high. Now we'll see third application. A diver performs somersault by jumping from a high diving board, keeping his legs and arm outstretched first and then curling his body. On doing so, the moment of inertia I of his body decreases as angular momentum L equal to I into omega remain constant. Therefore, angular velocity omega of his body increases. Look at here. The diver started jumping from the springboard. So initially the arms and legs are outstretched. That means these are limbs are outstretched here. And when he take this type of means his body, he curled his body like this, which is called the means this way. So the angular velocity will increase, because when the body is curled, when the arms are outstretched like this, the means arms are outstretched like this. So from the center of mass, which is at the navel, that is the distribution of mass at the maximum distance, and because R is maximum, so I will be maximum, then omega, that means the angular velocity will be minimum. So this time you will find that the angular velocity will be less, and as the body curl here, so when the body curl from the center of mass, this type the body curl, then from the center of mass the means distribution of masses, the distance of distribution of masses will reduce. When R will reduce, I also will reduce, and omega will increase. Omega will increase, that means the angular velocity will increase. So here you will see that this way, when the body curl, that is called the somersault, that means the angular velocity will be very high, and means at the mid of the journey the angular velocity will be very high. Then after that he then performs somersault as the diver is about to touch the surface of water. When he is touching the surface of water, again he is stretching his limbs, and so that the moment of inertia of his body increases and the angular velocity decreases, and so he can enter water with a little splash. So this way the whole means that when the diver performs somersault, that means in this way very safely he will land, or he will just enter into the water. Work done in rotational motion. work done in translatory motion, we are representing with the formula that work is equal to force into displacement. And we know that the rotational analog of force F is tau, that is the torque, and the rotational analog of displacement S is the theta, that is the angular displacement. So this formula if will change, then the work done will be, in place of F we can write tau, the rotational analog of force, and in place of displacement we can write theta, the rotational analog of displacement. So the work done for the rotational motion can be given by tau theta. And now we will see power in case of rotation motion. We know that the power is equal to work done upon time, and since just now we have seen the formula for the work done in case of rotational motion, that is work done is equal to tau into theta, where tau is the torque, that means the rotational analog of force, and theta, that is the angular velocity, is angular displacement is the rotational analog of linear displacement. Tau is called the moment of force. Okay, so the work done will be equal to tau theta. Now we know that for the small work done dw, suppose the time taken is dt, so the power can be written as dw upon dt, and we know that this is the work done. This work done is equal to tau theta. So in place of work done, if we'll write tau theta, so for a moment of means time being, tau will be as it is and only the theta will be changed. So we'll take the differentiation of theta. Tau will be constant. Tau is outside of the differentiation, and it is d theta upon dt. Actually we have replaced the value here, omega, with tau theta, and tau will come out because a constant quantity, and d theta upon dt will be there. Now we know that d theta upon dt is what? This is omega. Actually here I will just write this omega. This is W and this is work done. I am writing here W and this is work done. And this W, this is actually the omega, and this is equal to d theta upon dt. Omega is the angular velocity. So power is equal to tau omega, where we have replaced d theta upon dt with omega here. So power is tau omega. Now we'll see another formula of power. Once again we'll see the work done upon time will give us power, and for the small work done dw, again I am writing this the capital one so that we can differentiate between the omega and the work done. That means the angular velocity and the work done. So this is the work done. Now you will see that dw upon dt, that is the work done with respect to time, and we know that the work done is equal to energy, so we can replace work done with energy. So this is the differentiation of energy with respect to time, and the energy which we are taking here is the kinetic energy, that is half I omega square. We know that for the rotation motion the kinetic energy is given by this formula, so we have written here half I omega square. Now we know that half is constant quantity, I is constant here, moment of inertia. For with respect to time only the omega will change, so we'll take the differentiation of omega square with respect to time, and that will be equal to 2 omega d omega upon dt. Now half I and the differentiation of this is 2 omega d omega upon dt. This 2 would be cancelled here, and this is now I omega d omega upon dt, that is the angular velocity with respect to time, or we can say that the rate of change of angular velocity, that is equal to the angular acceleration, which is denoted with the letter alpha here. So alpha is the angular acceleration. This is replaced by this quantity d omega upon dt. So d omega upon dt is replaced by the alpha. So power is equal to now I omega alpha. So the one equation which we have derived here, that power is equal to tau omega, now here the power is equal to I omega alpha. So both the equation, if we'll write equation 1 and equation 2, if we compare, the power is given by the tau omega and it is also given by the I omega alpha. If you compare this two quantity, the omega would be cancelled. So tau is given as I alpha, and this formula already we have derived, the relation between the moment of inertia and the torque. So the relation between torque and moment of inertia is given by I alpha, and here we have seen the two formula of the power, here, that is power is equal to tau omega. In terms of moment of inertia, we can write power is equal to I omega alpha. Rolling motion is a combination of translation of the center of mass and the rotation of rest of the object around the center of mass. You can observe here the rolling motion is the combination of the pure rotation and the pure translation. In figure A, you will find the pure rotation. Figure B is representing the pure translation, and the combination of these two is represented with the figure C, and that will represent the rolling motion here. Here you will see in figure A that it shows the pure rotation as if axis of rotation through the center of wheel were stationary. This axis will be means through the center of wheel were stationary, and every point on the wheel rotates about its center with angular speed omega, and every point on the outside edge, this is the outside edge of the wheel, has linear speed VCM, that is the speed of the center of mass, VCM, that is equal to R omega, where R is the radius of the wheel. You can see that if this motion is the clockwise motion, in such situation, this top, you will see the velocity in the vector form in this direction, which is the same magnitude as the magnitude of the center of the mass. Here also you will find this is the top of the wheel and this is the bottom of the wheel. Here you will find in this direction the velocity, and it is the minus direction. That means the center of mass is moving in this direction only. Okay, so this will be opposite of that, but the magnitude will be same here. Now we'll see in the figure B. In figure B, it shows that pure translation as if the wheel did not rotate at all. That means we are not considering here the rotation motion of the wheel. Simply we are looking the translatory motion of the wheel here. So in that case, every point on the outside edge of the wheel moves to right of the linear speed VCM. Here you will see this is the VCM, that means the speed of the center of mass this side, right side. So at the top also you will find the velocity of the velocity of this point will be this direction, the magnitude will be same, that VCM. And here also you will find at the bottom also you will find the velocity will be as it is, like the velocity of the center of mass in the magnitude as well as in the direction. So everywhere, every point, the translatory motion is there, and every point is moving forward or in the right direction with VCM. Okay, now we'll see the combination of these two here in the figure C, and this is the combination of A and B. The figure C is the combination of A and B, and this represents the actual rolling motion of the wheel. And clearly the portion of the wheel at the bottom, here you will see at the bottom would be stationary, because if it is the sum of these two, you will find here at the bottom this direction the velocity is, and that is equal to minus VCM, and here you will find the direction is the right side, here left side and here right side. If you see the vector sum of these two, that will be cancelled here, and at the bottom you will find, that means the portion of the wheel at the bottom would be stationary, and the portion of wheel at the top, you will see that both the direction, this will be the sum of these two, the vector sum. So here also right side and here also right side, the same velocity is there, that will be add up and it will be giving us here the 2 VCM. So what we'll find here, the portion of the wheel at the top would be moving with a speed 2 VCM and faster than any other portion of the wheel. Now you will see that thus the velocity of a spherical body rolling over the horizontal surface without slipping goes on increasing from point of contact. This is the point of contact. From point of contact, here it is V equal to 0 to the topmost point on the periphery of the body. Periphery, that means this rim of the body, or the rim of the wheel, you can say, of the body, that is equal to V is equal to 2 omega r. Okay, so this is the rolling motion. Now we will see kinetic energy of rolling motion. As we know, the rolling motion is a combination of translatory motion and the rotatory motion. So the total kinetic energy of rolling body is given by sum of kinetic energy of translational motion of center of mass, represented with kT here, and the kinetic energy of rotation motion about the center of mass, that is Kr here. So the total kinetic energy is equal to Kt plus Kr, where Kt is the kinetic energy of translational motion of center of mass and Kr is the kinetic energy of rotational motion about the center of mass. We know that the kinetic energy of translational motion of center of mass is given by half m v cm square, where v cm is the velocity of the center of mass. Now we'll see that this is Kt. Now we'll see that the kinetic energy of rotational motion, the kinetic energy of rotational motion about the center of mass, is given by Kr is equal to I omega square, half I omega square. Now the rolling motion, in rolling motion the kinetic energy is sum of these two, Kt plus Kr. So the kinetic energy is equal to half mvcm square plus half I omega square. Now we know that this I omega square, here you will find K is equal to half. First of all, we'll take half common here, that is m, and VCM is given by here r omega. The VCM is given by r omega, or here we'll see, first I am just writing this as VCM square only, and half. Now we'll see that the I is given as mk square. What is mk square here? M is the mass of the body and k is the radius of gyration. This k, the small k I'll write here, that is equal to, the small k is the radius of gyration. And radius of gyration is nothing else, it is a perpendicular distance. The radius of gyration is the perpendicular distance of center of mass from the rotation axis that we have seen already. Okay, So this K is the radius of gyration here. Okay. Now this is omega. Here you will see that the omega is given as VCM upon R. Omega is given as VCM upon R, and the square of this will take. So here in this equation we have replaced I with mk square, where k is the radius of gyration, and the omega is replaced with VCM upon R. Okay, so we have taken the square of this. Now the kinetic energy. I am writing this as a kinetic energy, so there would be no confusion with the radius of gyration and the kinetic energy here. And half, we can take out half m v c m square. So what you will find, the first term here in this, nothing is left. That means the one that will be multiplied with half m v c m square will the same quantity, and plus half m v c m square already we have taken out. So this is k square upon r square. Okay, so this will be the kinetic energy. This is the kinetic energy of the rolling motion, that is given in terms of the radius of gyration and the velocity of center of mass. Okay, that is the velocity of the center of mass, and that we can write with the moment of inertia also. So this will be the formula for the kinetic energy of rolling motion. Now acceleration of rolling body. Consider a solid cylinder of mass m and radius r rolling down on an inclined plane of inclination theta without slipping. Look at here, this is the inclined plane. The length of the inclined plane is L, the height is h, and the width is b. The angle of inclination is theta. This is the rolling body. Initially it is at the top and at rest only. So here the potential energy is mgh. When it rolled down and reached to the bottom, so that time suppose the whole potential energy is converted into the kinetic energy, and the kinetic energy this time is given by the formula, that is half mvcm square 1 plus k square upon r square. So by this formula, so the potential energy is converted with this kinetic energy here. So we'll see, first of all, since sine theta is equal to base upon hypotenuse, sine theta is equal to perpendicular upon hypotenuse. So perpendicular is h and hypotenuse is L. So sine theta is h upon L. So h we can replace by L sine theta. Now as I told you from law of conservation of energy, the potential energy at the top is converted in the kinetic energy at the bottom. So you will see that the potential energy at the top is mgh and the kinetic energy at the bottom is half mvcm square k square upon r square plus 1. That already we have derived the formula for this, the kinetic energy, as you can see here. Okay, now that formula only we are using here. Here m and m would be cancelled. This g and h we will replace by this quantity L sine theta here. So h is replaced now L sine theta, that is m already it is cancelled. So VCM square upon 2 and k square upon r square plus 1. Now we'll just transfer this quantity to that side, and this quantity also that will come in the bottom. 2 will come up here. So V square CM VCM square, that is equal to 2GL. 2 will go up, 2GL sine theta, and that quantity will come down. Whether you will write it k square upon r square plus 1 or you will write 1 plus k square upon r square, no matter, means no difference is there in that. Okay, now you will see that all means already I have told you at the top of the this inclined plane, the body is initially at the rest. So the body start from rest. So the initial velocity will be 0. Now if we'll just apply the formula, that is v square is equal to u square plus 2as. So here you will see that the final velocity is vcm, initial velocity is u, acceleration here a, and the displacement is L here. So v square cm equal to u square plus 2al. U is 0. So vcm square is equal to 2al, or we can say the a is equal to vcm square upon 2l. That means if we'll go further from the equation 1, this is the equation 1, just divide 2l here. If you divide 2l here, you will get the acceleration. So v square cm will divide with 2l, that is 2 and l will be cancelled out. Then g sine theta upon 1 plus k square upon r square will remain. So I am just writing here from equation 1. From equation 1, as we know the formula, that is equal to what? V square cm, acceleration is given by 2l. So v square cm is what here? This is equal to 2gl sine theta and 1 plus k square upon r square. Okay, and here it is multiply with 1 upon 2l. So 2l to l would be cancelled. Acceleration will come here, that is g sine theta upon 1 plus k square upon r square. So this is the formula for the acceleration of rolling body, which is rolling without slipping in an inclined plane. So acceleration is equal to g sine theta upon 1 plus k square upon r square. This acceleration we can represent in terms of I, moment of inertia also. For that we'll just multiply and divide with the mass. So here it is mg sine theta, multiplication with mass is mg sine theta, and this will be this is m plus m k square upon r square. Now a is equal to mg sine theta, and this is m plus this mk square, mass multiply with square of radius of gyration, will give us I, that is I upon r square. So this will be another formula for the acceleration of a rolling body without slipping on an inclined plane where angle of inclination is theta, the mass of the body is m, and the radius of body is the r. So a is equal to, the acceleration is equal to mg sine theta upon m plus I upon r square.